Okay, if there's no questions, we can get started. So we were discussing about uh, approximating an higher order transfer function into a lower order. So let's continue with the discussion. We took the example of a second order system, or maybe, you can start off with any order system. S is equal to, and I took the example of a all pole system, that is no zeros. And I was trying to equate this to, or relate these two to one of the known transfer functions that we are familiar with from our UG control system courses. So we are trying to figure out that under what circumstances these I can neglect the higher order term, right? So in the context of, if I write h of s to be equal to 1 by d of s, where d of s is 1 plus b1s plus b2s square plus this. Right? So the question that we are trying to answer is that when can we approximate this? When can we basically drop these higher order terms and approximate this with 1 plus b1 of s? So to appreciate when we can do this, let's look at this transfer function, the second order transfer function. That will probably give us some idea as to when we can do this and when we cannot. So if I break this up into h of j omega, right? So what do I get? I essentially get, so this becomes minus omega squared by omega n squared, and together with the 1, it becomes 1 minus omega squared by omega n squared plus j omega by q omega n. And if I try to take the magnitude of it, right? So if I just take the magnitude, that is mod of h of j omega. Let me take the square. I do not want to deal with the under root and all. So this becomes 1 minus omega squared by omega n squared plus omega squared by u squared omega n squared. Okay. So now if I plot this, sorry, thank you. So if I plot this, so if I take a mod of, if I only take mod of h of j omega, not the squared terms, right? So if I plot this, so at DC, I mean, it's easy, right? At DC, I get 1. Now the problem is, I do not know what for a generalized Q, it is difficult to draw a plot because the Q can be more than 1, less than 1, 1, and so on. And depending on how the Q is, the plot can change a lot, right? So, but having said that, one thing we know for sure is at omega equal to omega n, right? At omega equal to omega n, what is the value of mod of h of j omega? Q, right? I mean, square is Q square, but this is Q, right? So let me just, yes. So if Q is more than 1, so this will probably be somewhere here. And beyond omega equal to omega n, far beyond omega equal to omega n, what will be the approximate transfer function? So at omega much, much greater than omega n, how can I approximate? Yeah, but which will be the dominant term? Yeah, the highest power will be the dominant term, and highest power will be, it's this omega squared by omega n squared whole square, right? And so which essentially means that your mod of omega, this one, will be omega n squared by omega squared, right? So so beyond omega n, I understand that this is going to go something sorry, if I am plotting only magnitude, it should not go negative. In dB, it can go negative. So this, and then it will probably asymptotically with a slope of, I mean, with this profile, 1 over omega square, it will go to 0. So basically, I understand that it will probably go something like this, and then go like this. And this ratio is what? This ratio is? So in other words, what will be this value? Q, right? So Q, assuming that this is 1. Right? If that is not 1, then it will scale basically, right? So your the amount of peaking that you can have in your transfer function, a second order transfer function, gives you the Q of the network, right? If we go by the definition of Q in the second order transfer function. Yes.
Right now, it's not defined for closed loop or open loop system.
No loop, just a transfer function. Just a transfer function. Nothing to do with closed loop, open loop. We haven't even touched that. So, now essentially, the point that we should be mindful of is, just like the time constant doesn't have any meaning unless it's a first order circuit, right? If you have a higher order circuit, you cannot, the meaning of time constant is not valid, right? In order to have a time constant, you need to have one capacitor or one inductor, and then the Thevenin equivalent resistance across it, right? So then C times the Thevenin, or L divided by the R Thevenin, is essentially the time constant. If you have more C's and more L's, more than one, then you'll not, the concept of time constant itself is not valid. Just like time constant is valid, the concept of time constant is valid strictly for a first order system. This definition of Q, that is the peaking with respect to whatever you are happening at low frequency, is valid only for second order system, second order low pass. Okay. So, but having said that, just like if you can neglect higher order terms, you can probably reduce a bigger circuit into a first order circuit and then associate a Q time constant to it. Similarly, if it is possible to neglect higher order terms and reduce a circuit to a second order circuit, I can associate a Q to that, right? So now, so that is, the caveat is you need to understand when you can neglect and when you cannot. Okay. So now let's come back. I mean, I will not concern myself with higher order transfer function more than 2 at this moment. But if we have to continue the discussion started because we wanted to convert everything to a first order system and see when we can and we cannot. So now so if I say that if you have a first order transfer function, which will be of this form, let's say 1 by 1 plus S over P. And if I plot the mod of H of j omega of this, so this will start off with 1, and at very high frequency, this will go off as, so this just like this goes as omega n squared by omega squared. At very high frequency, what will be the slope? P by S, right? P by omega, essentially, right? So this will be P by omega. So at very high frequency, clearly it doesn't match. The second order approximation, the second order transfer function approximated to first order doesn't match, right? That should be expected because at high frequency, I would expect the higher order terms to dominate. And in a first order approximation, I do not have any higher order terms, right? So that's why in a high frequency scenario, your higher order, first order approximation is going to break. That is fine. At low frequency, I would expect them to match because I can, at 0, for example, at DC, I do not have to bother with any higher order term, right? So because at 0 frequency, both the DC, both the first order and the second order, in both the cases, I can neglect any function of omega, they match perfectly. So now as you go from DC to higher order, higher frequency, the deviation will start to become higher and higher, correct? So that we understand intuitively. Now the question is, using a first order circuit, can you ever have a peaking in the transfer function of more than 1. Which means I'm a low pass, right? I mean, I'm only talking about this kind of transfer function. It cannot ever go, right? So it can only go down, right? So it can only go down. So now, depending upon what is the value of P, it will start to go down at a specific frequency, which we can call it as a 3 dB. Right? Now, the question that we are trying to answer is, under what condition this guy matches a first order transfer function? Correct? So now I will call upon your knowledge of control system, second order roll off and all. So are you aware? I'm pretty sure you are, but just to refresh, you have these concepts of overdamped, underdamped, critically damped transfer functions, right? So can you comment that if I have if you have a Q of more than 1, firstly, if a Q of more than 1 is between the 3 conditions, which condition will it satisfy? Underdamped, right? Underdamped. So which means that in underdamped condition, we will never be able to model as a first order response. Correct? What about critically damped? Q is equal to 1, right? Where Q equal to 1 means it's better modeled, right? But it will not peak per se. But it will do something like this, right? And if you have overdamped, then definitely, I mean, it will damp out pretty quickly, right? So obviously, between the 3 cases, which one can you model as a first order response? Better. I mean, never 100% you'll never be able to model, but overdamped, right? So which means that whenever you are approximating a transfer function, right, which is low pass transfer function, which is given to you, you want to understand whether I will have, if I drop the higher order terms, I will be incurring how much error, then you probably will have to understand whether there can be a peaking in the transfer function or not. Right? If you do not have any peaking, sure, go ahead and model it as a first order system. If you have a peaking, no, you cannot. Then you have to probably take at least second order, right? And then break it up into multiple. You know, like zeta, Q, and all those things. Then you do your analysis. Okay, so that is something that we should be mindful of. Okay, any other questions so far? No. Okay. So the next thing that I would like to draw your attention to is, this is also a part of one of the questions, that we have so far done analysis using mostly capacitors, right? Capacitors and resistors. Control sources also doesn't make any difference because they fall. I mean, when you are calculating impedance, they will also give you some Thevenin equivalent resistance and you use it. But what about inductors? Right? So if you have inductors in a network, does the analysis change in any way? It should not, right? Because we did not necessarily assume we did not necessarily assume anything particular to a capacitor, any particular property of a capacitor in order to arrive at the framework, right? The only property that we used is when we set the capacitor value to 0, we are opening it, and when you're setting the capacitor value to infinity, we are shorting it. That is the only capacitor property that we have used. But mathematically, from an algebraic standpoint, it doesn't make any difference if I replace all the C's with L's. Correct? So which essentially means that I do not have to change the framework. All we have to do is to find out an equivalent framework for, from the circuit standpoint, you have to find out an equivalent framework in order to quickly find out those effective time constants. Correct? So if I write out the time, again, it's the same thing. If we write it out, what do we get? We got H0 by 1 plus, here we got tau I 0 times S. This is and here we got This was H2J or H2I? What was it on the subscript, superscript? IJ, right? So while these transfer constants are always easy way to remember is that transfer constants are under the condition that whatever you have on the superscript are shorted. I mean, set to infinity. I shouldn't say shorted now because now we are moving on to both capacitors and inductors, right? When the thing on the top is set to infinity. Now, whatever the infinity will do to that element is particular to that element, but algebraically this is set to infinity, right? So now, so if I have now again, if I have a capacitor, we know what to do. If I have an inductor, how should I go about framing this? Let's say I have an inductor L1. I want to start off with finding out this term. So I will, so let's take an example, right? Instead of doing it generic, let's take an example. I call this L1, I call this C2, just to make sure that indices are taken care. So if I want to find out, so n equal to how much? 2. Okay. So I should have tau 1, 0 and tau 2, 0, right? Okay. What will be tau 1, 0? Okay, let's do tau 2, 0 because we are using capacitors are probably we are more familiar with. So tau 2, 0, which means what is by definition, what are we doing? So we don't need this. This is shorted, right? And we are considering the time constant associated with the capacitor while everything else is 0 valued, right? So which means this is L is shorted. So tau 2, 0 will be RC2. Okay. What about tau 1, 0? Again, the same thing. We are dealing with L when everything else is 0 valued. It is C2 is open circuited. So what will be tau 1, 0? Now note that for an inductor, your time constant is L over R, right? So what is the effective R across the inductor? Infinite. So tau 1, 0 will be 0. Okay. What about so I get the first term. So your B1 becomes RC2, right? So I want now this one, let's say. So this will be how many terms? Only one, right? So I can have tau 1, 0, tau 2, 1, or I can have tau 2, 0, tau 1, 2. Correct? So tau 1, okay, let's do this bottom one first, okay? Then we'll see the top one. So if I do the bottom one, so tau 2, 0 is RC2. What is tau 1, 2? What is meant by tau 1, 2? Yeah, we are bothered with this element, time constant associated with this element when everything else is set to infinity, right? So C2 is set to infinity, which means short circuited, which means your time constant tau 1, 2 will be, or tau 1 superscript 2 will be L1 by R, right? L1 by R. So this becomes L1 C2, correct? So I should get the same thing if I use this also, right? Right? I can do either in principle. But the issue here is, firstly, this guy is 0, right? So what is tau 2, 1? Why? Right, yeah, right. So tau 2, 1 means I am interested in the capacitor while everything else is infinite valued, which means L1 is infinite valued, means open circuit. Right? So that is set to infinity. So this sets to infinity. So obviously 0 into infinity, I mean, it can be anything, is difficult to compute. So that is why when you are doing things with inductor capacitor put together, you better not choose your taus appropriately. So if you do not want to, I mean, if you want to be rigid about it, you can get around this problem by putting a resistor here. Let's say, I don't know, R infinity, and do your calculation using R infinity and then set R infinity to 0, infinite, right? So you are going to get the same result, but it's more algebra. Okay, so the point that I'm trying to make here is that the framework is fine, but the ease of application of the framework depends on the user. You have to be smart in choosing which time constant you are going to use. Okay.
Can you explain D1 to again?
You mean this one?
D1.
This one? Okay. So by definition, what is tau 1, 2? So this means that I am interested in the element which is marked with index 1, right? So element having index 1, while the element having index 2 is infinite, right? While their element with index 2 is set to infinite, and all other elements are 0. We do not have all other elements here, but if we have all other elements are 0. Right? So now if I do that, so what is the element having index 1? That is L1, right? What is the element having index 2? That is C2. If I set C2 to infinite, that gets shorted, right? So I get that your loop becomes this. So this effectively under this condition, whatever I am whatever time constant I am getting is tau 1, 2, which is equal to L1 by R. Right? Okay. Any other question? Okay. So now let's move to another way of intuiting. Oh, by the way, I mean, I have not completed the thought here, right? So here I got this term, here I got this term. What about the numerator? What is H0 or H0? H0 means what? You zero value all memory elements. So L1 is 0 means shorted. C2 is 0 means open. So essentially, by the way, when you are doing zeros, the position of the input and the output are important. So what will be H0? 1, right? Because L1 is shorted, C2 is open. So this is 1. What will be H1, 1 and H1, 2? So H1, 1 by definition should mean, basically I'm trying to find out the coefficient of S in the numerator, that is this one, right? And on the superscript I have 1 means I am infinite valuing that index, right? So if I do that, what will be the output? Everything else is 0 valued, obviously, yes. 0, right? So open circuit between, from here to here, you have open circuit. So this becomes 0. What about H1, 2? I mean, infinite valuing what? C2. If I infinite value C2, then obviously, what will it be? 0. Why? Why 1? So if I infinite value C2, what happens? What does the circuit reduce to? correct? And L1 obviously is zero valued, right? So that it goes without saying. Anything that is not present in the numerator is I mean, in the superscript is zero valued. So this is also zero, right? So your that term also goes. What about H2 1 2? This should be very easy, right? H1 of 1 will be 1. Why? So H1 of 1 means what for here? So I have this. L1 is no. Well, H1 of 1 means inductor, infinite valuing the inductor. Correct? So this is open. And C2 is 0, which means that is also infinite valued. Sorry, zero valued open. So don't have anything, right? Obviously, I mean, one might say, what about the initial condition and all, right? So this is steady state, no initial conditions. Okay, fine. So what about H212? I mean, if either of other two cases are 0, obviously H212 will also be 0. So you ended up with first order. I mean, numerator is only 1. Denominator you have 1 terms of S and terms of S square. I mean, that is expected, right? So you get 1 over 1 plus RC2 S times RC2 plus S squared times L1C2. So that is, I mean, I'm pretty sure you know this because it's a standard circuit that you have seen multiple times before. Okay. So now let's focus on and the second thing, that is, how do I know how by inspection of a network, how many zeros are there? Question? Okay, so by the way, before going there, how do I know by inspection how many poles are there? I think I referred to it multiple times before. Correct. No, it's not the number of energy storing electrons. Yeah, all of you are saying more or less similar things, but if you have to nail it down, it's basically the number of independent initial conditions that you can set. Right? If you have, for example, I mean, the trivial things are, if you have a network which is like this, even though you have two capacitors, you cannot set more than one initial condition, because the moment you set a condition on this capacitor, the other will get set, right? What about this guy? By the way, the order of a transfer function does not depend upon where you apply the input. Okay, so that is something because it sets the new denominator, the auxiliary transfer or auxiliary function, or rather auxiliary equation. What about this? What is the order? Second. First or second? Why first? Why second? I can combine C1, C2, sure. But if I go by that logic also, saying that I can also set initial conditions separately on C1 and C2. It doesn't depend upon, right, where you take the output. So strictly speaking, this is a second order circuit, right? So, and the reason you get, if you apply, for example, an input here, you do not see a second order response is because we can argue that the zero and the poles cancel. Okay. And if you are not convinced, what you can do is set up, you can do, I'll not show you here, but you can do the math. Set up a initial condition on either of these capacitors, C1 and C2, and write down the differential equation and see how the system evolves. You'll see it's not a first order decay. You do it yourself once. Okay, so the key thing to note is the number of initial conditions, the number of independent initial conditions that you can set in a network sets the order of the network. It's number of poles, right? If you have less, you cannot have more. If you have lesser, which means that from there itself, you will understand there is probably a zero which is cancelling one of the poles. Okay, this is the maximum order. And so sometimes you get networks like these. What is the order of the system? Yeah, you have done 610 before. So why second order or why not third order? Come again? No, without transformation. Let's say I do not do.
Initial conditions on true capacitors automatically.
Exactly, right? So if I set the capacity, this initial condition, the initial condition across C3 gets set. That's not an independent initial condition. So hence its order is 2. Okay, fine. So so this is order is 2. Fine. So we understand how to set the how to find out the order of or rather how to find out the number of poles. But what about the zeros? So that is not so obvious. So in order to find out, in order to explicitly find out whatever the number of zeros is there, so I will again go back to this framework. So we have 1 plus B1S plus. Now, let me use some other term. Say AM is to the n. So if the this transfer function has, let's say, 2 zeros, and the denominator is, let's say, of 10th order, what will the numerator look like? Will the numerator also have 10 terms? No, obviously no, right? How many terms will it have? It will have 3 terms, and the maximum will be A2. Correct? So essentially, if the coefficient of, so I have to basically find out the coefficient of the highest order of S. Right? So in other words, if the coefficient of the highest order of okay, let me rephrase. So the if, let's say, the coefficient of S to the power m is non-zero, right, and everything else above m is 0, then I can say that the order of, or the number of zeros in the system are m, right? So essentially, I have to find out a way of figuring out what is the highest non-zero coefficient, right? If I have to be more strict, I have to say that I have to find out what is the coefficient, non-zero coefficient for the highest power of m, highest power of S. So if I can find that out, that power will be the equivalent of the number of zeros that I have, right? So now what is this AM? So AM, in AM, what do I have? I have this bunch of time constants which are anywhere there in the denominator. They are not going to go to 0, right? But the stuff that can go to 0 is this multiplying factor, correct? So you have HM and you have here I, J, K, everything, right? Up to M, right? And what does this numerator superscript mean? All of them have been set to infinity. So in other words, if I have a network where I can set, let's say 3, I mean, just to take an example, if I have a network where I can set 3 elements to infinite and get non-zero output, right? Then what can I comment on the number of zeros? what I'm essentially saying is that let's say I have a network where A3, or rather where H3, then I, J, K, blah, 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 is not 0. At least 3 zeros will be there, right? And if I say that everything higher, right, all H4 and everything are 0, then I can say that only 3 zeros are there. So in other words, if in plain English, the number of zeros in the system is the number of memory elements I can infinite values simultaneously while not getting 0 output. Right? So now, essentially in the transfer function, I should be in the network, I should be able to infinite value some number of elements while not getting 0 at the output. So that value is essentially your number of zeros. Correct? So when I say it in English, it probably sounds more convoluted than it actually is. But if we see it in an example, it will be much easier to appreciate. So let's say I have this. What is the order? Third order. Good. Now I want to find out the number of zeros. So how many elements I can simultaneously infinite value in order to get a non-zero output? So it's better to start off with doing one at a time. So if I infinite value C1, let's say now my output is here. Okay. So let's say I infinite value C1, will I get a 0 output or non-zero output? I'll get a 0 output, right? If I infinite value C2, same thing, right? If I infinite value C3, while keeping C1, C2 finite, I'm doing only one at a time now. If I infinite value C3, I'm going to get an output, right? So number of zeros is at least 1. That much I have been able to establish. So now next thing to establish is whether can it be more than 1. So if now I take 2 at a time, right? So if I infinite value C1, C3, output will be 0 or non-zero? 0. If I infinite value C2, C3, 0. C1, C2, 0, right? So if that combination doesn't hold, I mean, there's no point in going to higher. Right? So I can stop and say that the number of zeros is 1, right? So similarly, you can go about figuring it out. Similarly, I can also say that what about if I don't take the output from there, I take the output from here, right? So now, can the number of zeros change? Of course, it can change because the numerator, I mean, where I take the output has a significant impact in the transfer function. So how many zeros can it have? So if again, we do the same thing. If C1 is set to infinity, I get 0. So not possible. C2 set to infinity, I can have non-zero, right? C3 set to infinity, I can have non-zero, right? So fine. So at least I know first order I'll have. At least 1 0 I am going to have, right? What about number of 2? Can I set 2 elements to infinity? C3 and C2, if I set to infinity, then I can also have non-zero. Can I set 3 to infinity? No, right? So basically it has number of zeros will be 2. Right? Make sense? Okay. Okay. Fine. So the next thing is, so let me now focus on first order transfer functions back to first order. So let's say, because ultimately we would want to ultimately reduce the order, if not first order, maybe second order. So, but let's come back to first order. So let's say I have a transfer function which is something like this. Let me not write it in this format. So just write. Okay. And if I want to write in that format, this will be, sorry, this will be A0 plus. So it will be H naught. If this is a strictly first order network, then B1 will have how many terms? I equal to 1 to n will be equal to 1, right? So essentially I'm going to have one term, right? So I'm going to have one time constant. Yes, and in the numerator, I'm going to have same H1 times tau s, right? So I can break it down into two formats. I can break it down into right? And this second term, I can break it down further, or reduce further as so. If we now, for the time being, let's concentrate on this term, right? And now I am interested in, let's say, the step response of this transfer function. Okay. So, when you have a transfer function, you can typically we either are interested in a step response or the sinusoidal steady state response, right? For sinusoidal steady state response, that h of mod of h of j omega and all those things are important. For step response, time constants are important, right? So here, what will be the step response of this guy? Input is a step, so output will be. So this is of this form, right? 1 by 1 plus s by a, s plus a, right? So what is the step response of that guy? Yeah, so what I mean is, will it be like this or will it be like this? Black one, right? So it will go, it will be something like this. And it will reach to what value? H naught, right? And its time constant obviously will be equal to tau, correct? What about this guy? Huh? It will be only decay, right? Somebody said only decay, right? So it will be only decay. Sure, it will be only decay. And so something like this. But where will it start from? H1, right? Yeah. So it will start from H1 and it will decay with the same time constant, tau, right? Okay. So now when I am adding these two up, right? So this essentially means that I'm adding the step responses of this and this up also, right? The step response is basically I take an inverse Laplace and it's a LTI system. I can take one at a time and add them up, right? So if I add them up, what am I going to get? By the way, I have not talked about whether H1 is positive or negative or H0 is positive or negative, right? So I've just drawn it like this. It can be either. So assuming it is positive, it would look something like, and depending upon value of H1 and H1, that is also I have not talked about. So it can be anything. It can look like this. What is going to happen? So what will be the step response for this equivalent if H1 is negative? It will start from negative, right? It will start from. And if I add them up, the total So this is, I should say, this is combined, right? This is combined. Case 1. This is combined. Case 2. Possibilities need not necessarily be that these are the only two possibilities, but yeah, you can have a dip and come up and all those things, depending upon the values of H1 and H0. So now if H1 is less than 0, what will be the combined case 3? Right. So it can start, basically your output can go something like this and then go like this and eventually settle to H0 to start with H1. So it always starts with H1 and ends up with H0, right, in a first order system. Now, depending upon whether H0 is, I mean, the signs of H0 and H1 are same or not, right? So that depends upon whether they are starting from the same side of 0 or opposite side of 0. Now, this might seem trivial, but this has deep impact because let's say you are trying to design a circuit in which the step response has to be maximized, right? Or you want to make the step response as fast as possible. Okay. So then which one would you prefer? Let's say you have the choice between this guy and this guy. So clearly the first one you would prefer because it looks like it is pushing it high. It can reach I mean, whatever, it never reaches 1, but let's say you say I want to reach 90% of the final value. So clearly the first one will reach there faster than the last one, right? So now, now if I go back and see the transfer function, what does it imply as a transfer function level? So if I see that if H0 and H1 is, basically H0 and H1 is more than 0, which means they have the same sign. If that is the case, what can you comment on the location of the 0 with respect to which side of the right half plane 0 or left half plane 0, right? Because your H1, your 0 location is what then? How do I know the 0 location? So I set this to 0. So S is equal to minus H0 by H1 down. Correct? So if H0 and H1 have the same polarity, right? So you have a negative half plane, I mean, left half plane 0. And this is not only useful for finding out the location of the zeros, but you see there is a direct impact in terms of the final settling of the system, right? So if you have a left half plane 0, firstly, if you do not have, let's say you only have the step response plot and you have to infer whether you have a 0 or not. Let's say you know that it's a first order network or rather any other order network. You want to infer firstly whether you have a 0 or not from the step response. What is the first thing that you're going to look at? How is it starting, right? So if it is starting from non-zero value, then definitely in the transfer function you have a 0. Otherwise, it's not possible. Okay. In a first order transfer function, that you can, I mean, definitely say that. Yes.
Higher orders, like zeros is there.
We'll come to that. We'll come.
By graph, we can.
Yeah, you can. We'll come to that. So the other thing that you can, so okay. So what was? Okay. So the next thing that you can, figure out from the plots whether you have a left hand pole, LHP or RHP, left half plane, right half plane. Sorry. So your whether the 0 is in LHP or RHP, you can figure out how the step response starts, right? So if it starts from, if the final value and the initial value are in the opposite direction of your starting point, right? So then you see that the 0 would be in the right half plane. Now when you are designing networks, sometimes we do not look at the phase plot of the zeros. I mean, if you only look at the magnitude plot, you are only going to get the values of mod of H1 and mod of H0. You are not going to get the sign of it, right? So if you are not careful, what might happen is if mod of H1 and mod of H0 are same, and you are finding out the transfer function, and you are only looking at the magnitude plot, they will look identical, right? You might two designers can come up with f(h) of s having same magnitude of H0 and H1, but opposite in sign. Their magnitude plot will look identical, but their step response will look completely different, right? Because you did not take into account the sign of the zero, which half plane the zero is. Okay. So this also has an impact on figuring out what is the. By the way, I mean, before I go forward, any questions so far? How much time we have? Yes.
Kind of number of C.
Hmm.
What is like for m elements set to infinity, we get one positive, and for another set of m elements, we get negative, and it cancels out.
So number of zeros will not get cancelled out, right?
There is summation of h storing.
Uh-huh.
So one h is positive, another h is negative.
Okay. Let's think about it. If you're saying algebraically, yes, that is possible, right? But I'm trying to understand physically, will it be possible? So you're saying that, let's say I have Cij, for some value of ij, I am getting some H2. For different value of ij, I get another H2, which is negative, right? That is possible. Still, in that case, your number of, zeros will be, okay, so this framework is essentially telling us that I have to find out zero a power, which is the highest a power m, s power m term, right? So in that framework, that will not work. You are correct. So it is possible to come up with a network. In principle, at least algebraically, we can show that for let's say C1, C2, you get beta ij to be equal to +1, and another same value of C3, C4, where C is equal to C1, C2, beta ij is equal to -1. Yeah, I don't see why we cannot construct a network like that. In that case, you should get that order of zero can get cancelled out. That's what I'm saying. Yes, that can happen. So in that case, you'll not be able to find distinctly say that is the number. Okay, so the argument against it will be so it depends on then the value of the capacitance, value of those elements, right? Yeah, right. So not the location per se.
From this method, you will find more number of zeros than the.
No. What do you mean by more number of zeros than poles?
More number of zeros than it is present in the actual system.
If we just limit ourselves to number of simultaneously infinite valued, it is possible. Yeah, I agree with you. It is possible because you can have negative HM, right? So it is possible that it might cancel out, and eventually we have lesser number. But the argument against it will be, even though it's not a very strong argument, the argument against that will be the zero location will also be dependent upon the values of the C's, right? Or will it? It will, right? Because the time constants are dependent upon the values of the C's, right? So if the time constants are dependent on the values of the C's, which means if I change the values, that cancellation might not work. No, I mean, we can obviously work backwards and come up with, but it will not be true for a generic, for a same architecture. I can change the values of the capacitors, right? I'm not changing the architectures. So I can change the values of the elements. All finite valued, I'm changing them. If I change them, then the time constants change. The value of the time constants change, right? So for a particular architecture where I can get that cancellation to happen, I just change the values of the element and the right. So that way I would argue that the number of zeros are still not changing. So I would say that this can give you, if I then have to be rigid about it, I have to say that this gives you the maximum number of zeros that you can have. It can be lower than that if cancellation hasn't happened, right? But that's a very good point.
Same power of S, right? For S.
Correct. Same power of S. So do all of you follow the question? Okay, this question was this, right? So let's say I observe, I have C1, C2, C3, a whole bunch of capacitors. I have, let's say, control sources. Let's say only this, multiple control sources, and so on. So it is possible. I mean, I am going to get terms of C1, C2, beta 1, 2, then C2, C3, beta 2, 3, C3, C1. In the numerator, if I concentrate, C3, C1, alpha 1, 2, alpha 2, 3, alpha 3, 1. And all of them will have SS squared, SS squared, SS squared. Correct? So his point is, let's say, is it not possible that for values of certain values of C1, C2, C3, C1, all of them, while individually becoming non-zero, they cancel out, because now I have the option of these to be negative. Beta ij cannot ever be negative because they are all time constants, but this alpha 1, 2, alpha 2, 3, alpha 3, 1, they can be negative, right? Because it's from input to output, depending upon how the control sources are arranged, it is possible that it can go negative. Correct. So is it not possible that when I connect all of them up in certain values of C1, C2, C3, I can always come up with, right, that they go to zero, right? Algebraically, I do not see why it cannot go to zero. They can, but they will probably go to zero, but set values of C1, C2, C3. If I change it, make it generic, they will not go to zero, right? So that's why I'm tempted to say that it's a more rigid condition, in the sense that you cannot have more than that, but maybe you can have less than that, right? So I have to think about it deeply whether this has, is there any mathematical theorem in polynomials, transfer functions, where this is not allowed? But standing at this moment, I cannot really think of. Yes.
Basically, if they all cancel out, that means you will not be able to determine the number of zeros while just looking at the circuit.
No, I would argue that you still can, because for a generic value of C1, C2, C3, you will be able to. Just that for a particular value, that zero vanishes. So it's equivalent. Yeah, right. So it's equivalent to saying, let's say you have a pole zero cancellation. You have a pole and a zero at the same location. You can still cancel out, but the pole exists, right? The moment if you change certain value, the zero shifts away from the pole, it will appear. It is being masked. That is similar to this, right? But I have to, I mean, to be honest, I have to think about it a bit more deeply to give you a more concrete answer, but very good question. I have tempted to say that, I mean, my follow-up is essentially that when it cannot be true for all values of C1, C2, C3. If that is not the case, then I would stick to that number of zeros is that. Okay.
So
yes.
Give an example where transfer constants are negative.
Okay, good, right? So maybe it was one of the assignment problems, but we can do it here. So let's say I have, so when I say transfer constant can go negative, what I'm essentially saying, I am saying that H0 sets the final value and H1 is setting the, in a step response, H0 sets the final value and H1 is setting the way it starts, right? So all I have to do is set up a circuit in which the final and the initial go in the opposite direction. Correct? So obviously, if you have only RCs, it's probably not, you cannot do it because everything goes in the same direction. But if I use a control source, then it is possible, right? So for example, I mean, the simplest thing you can think of is, let's say you have something like this, let's say. Right? So in this case, your H1 is, can you comment H1 is positive or negative? Oh, I have not told you where the V naught is. So it's V naught. Positive, right? So I have to now set it up in such a way that there is an H naught which is negative. Then I am going to get this opposite side 0. So how can I set it up? I cannot connect anything from here to there directly because that will also have the same sign of H naught. So I have to do a flip, polarity flip. If you have control sources, that polarity flip is possible, right? An example is, let's say I do this. Let's say I call this V1 and I call this G times V1, where G is more than, G is positive. So what will be H naught? So here H1 is 1. What will be H naught? So C is not there, right? G into R2 will be the magnitude and polarity. Minus G into R2, right? So in this case, clearly you will have a right half plane 0, right? And it will have all the bad things that we're talking about. But yeah, good question. Any other questions? Yes.
Essentially, having a negative H1 would mean that you are involving a right half plane variable.
Yes, so not negative H1, negative polarities between H0 and H1. So basically H0 times H1 has to be less than 0, right? So in that case, you have a right half plane 0. Both can be negative, fine. Yeah, I mean, your final value is negative. Possible, right? Okay. So we covered this. There is one more thing I wanted to cover. What was that? So the last thing that I like to cover in first order circuits systems is this. So it is trivial to say that if I have a network, which is the transfer function 1 plus tau of S, its bandwidth is effectively is omega 3 dB is how much? 1 over tau, right? So what about if I have a network which has a 0, let's say. So if I write it in this form, A naught So how do I estimate the bandwidth? So again, I do not want an exact bandwidth, I want an estimation. So clearly, if I just say that it also has a bandwidth of 1 over tau, there will be error. I want a slightly better estimation, right? So I can basically say this is equal to, I find out the 0. So how do I get the 0? So I say A0, 1 plus A1 by A naught S by 1 plus tau S. So I'll write it in this form so that it becomes easier to comprehend. S by Z by 1 plus S by P. So this I can approximate as saying 1 by right? Okay, so if you are not readily solved, I can say this is equal to so I do a Taylor series and return the first order terms. So this is not approximate, this is exact. This is approximate. Right? So again, another set of approximation, 1 by 1 plus S by P minus S by Z. Correct? I can do that. So yeah. So again, so all those approximations, right? So erroneous, but still a better situation than earlier, right? So your this is essentially so what is your 3 dB bandwidth then? Yeah. 1 by P minus 1 by Z. So the caveat here is when we say 3 dB bandwidth, we are only talking about magnitude. We're not talking about phase, right? 3 dB bandwidth only talks about magnitude. But what about if Z has same value but opposite phase? Then the 3 dB bandwidth should not change, isn't it? In any system, the 3 dB bandwidth should not change based on the polarity of the zero, because polarity of the zero does not change the magnitude. It only changes the phase. We agree with that, right? So which means that in principle, the magnitude part of your plot should not change, which means the 3 dB bandwidth should not change based on the polarity of the zero. Correct? But this expression, even though I am claiming this to be slightly accurate version of the pole of the bandwidth, can still be quite wrong if Z has different polarities, isn't it? So a better way to go about dealing it is not to take the polarity of the Z and say that this is always mod of Z, right? So because if I have a 0 in the numerator, it is always expected to increase my 3 dB bandwidth. Correct? Phase something is a different story, but if I have a 0 in the numerator, I mean, if you are confused, then you can plot it out. So let's say this is your first order plot, which is 1 by 1 plus S by P. If I have another plot which is 1 plus S by Z, and I'm not commenting on the direction of the 0. So clearly this will be for every value of omega, I am beyond omega equal to 0, I'm going to have a higher value, right? So of H. So I'm going to get something like this. I mean, how far it will go up and down is dependent upon the value of Z, but I'm going to probably get something like this. And this is independent of the polarity of Z. Correct? So regardless of whether I have a light up plane 0 or left up plane 0, I'm always going to get increased bandwidth. Right? So that's why the approximation is this is 1 by mod of Z. Right? Again, very crude level approximation. These are all useful if you want to get a quick and dirty estimate of what is the bandwidth of your network. Right? Not necessarily exact, not necessarily to understand what is the exact bandwidth. Okay. Okay, fine. Let's stop here because out of time. Any questions? Maybe we can take one question before we break.
That is P.
Pardon?
That is P.
Then obviously this is not valid. I mean, this approximation itself will not be valid, right? So all of these are valid when you can neglect so many higher order terms, right?
In the approximation or assumption that you use this, that Z is much larger than.
Yeah. Yes, correct. That is correct. Okay, fine. Then we'll stop here. Thank you.